Hi. Okay, great. Hi. Okay, hi everyone. Welcome back to the course. Last time we talked about backpropagation at the end of the class. Let's review that again because it was a bit fast. So let's do that again. By the way, before we start, any question? No? Okay. A neural network, let's consider a fully connected neural network with, you can see it as, you can see each of these as one layer. So this is just convention. Either each of these as one layer or each of these as one layer, doesn't matter. Naming is not important. Mathematics behind these are important. So for now, when I'm talking about layer in this backpropagation algorithm, which I'm talking about, I mean this. So I mean, this is a layer, this is a layer, this is a layer, this is a layer, okay? Now, these are the weights between the layers. Every neuron in neural network, you can see it in this way, right? So you have, let me clear this. Let me clear shape and also here. So what do we have? We have the outputs of the previous layer, and these are the weights. Here in this slide deck, I'm showing the weights by X, but you can show them by the W, whatever. Again, naming is not important. So Z is the output of activation function, okay? And X's are the weights. What? Okay. Sure. Yeah, if you would like, you can sit in front. That's fine. So Z is the output of the activation function, okay? And X is the weights of the layers, and AI is the before activation function. We feed AI to the activation function, we get Z. And as you see, we have Zs here from the previous layer. We also have Z in this layer, which goes to the next layer, okay? So as I told you, AI is a linear combination of the Zs of the previous layer, where XIL here is the weight. And what is XIL? So XI1 connects Z1 to AI. Why don't I name it X1I? Because it's easier in notation of backpropagation to denote it by XI1. Usually people do that. Okay, so XI1 connects Z1 to AI. And I is the index of the neuron in this layer. Okay, and L here, this L goes from 1 to M. This is the index of neurons in this layer. Okay, assume we have M neurons. And Zi, you feed AI to the activation function of the ith neuron, sigma I, and it gives you Zi. An activation function, usually, except some exceptional cases which we talked about in the previous session, they usually get a scalar and they output a scalar if they are applied on one neuron. Okay. And then we talked about it. We said backpropagation is nothing but gradient descent and chain rule, right? So let's see that. So consider three layers: layer L, layer I, and layer J, right? So and here this is layer L, but I index its neurons by L2. This is layer I index its neurons by I, and this is layer J, I index its neurons by J, right? Okay, now, as I said, this is XIL because it connects ZL to AI. This is also xji because it connects zi to aj, right? Now we have ai equals summation of xil zl. What do I mean? This ai is the output of the neuron, the previous layer, times their weights, and we sum them, right? This is what we had here. What we had here too. Now it sums over the neurons in layer L. Okay, by chain rule, what do we want? We want the gradient of the error with respect to the weight. Actually, what do we want to learn? What is our optimization variable? Every weight, right? What are the learnable parameters which we want to learn in neural network? The weights, right? Here, xil, xji, all of them are our optimization variables, right? So we want to learn them in optimization whenever we have a cost and we have some optimization variables. What do we do if it is unconstrained? Yeah, we exactly differentiate. We take derivative and set it to 0. Okay. So this is the first order optimality condition. This is exactly what we are going to do. Assume error is denoted by E, and we take derivative of error with respect to every single weight, right? For the last layer, it's easy, we'll see. But for the middle layers and the initial layers, they depend on the next layer. So we need to have chain rule. And as for the last layer, it's easy. We start from the last layer and we come one layer back at a time. And that's why its name is backpropagation, because we are propagating backwards. Okay, we are backpropagating the error in this way. Okay, derivative of error with respect to xil is what? We can write it as derivative of error with respect to ai times derivative of ai with respect to xil, right? We can write that. What is the derivative of ai with respect to xil? Let's find that. So we know that ai here is summation of xil zl over L, right? We know that ai is the summation of outputs of these neurons times the weights here. Okay, and now what I want derivative of ai with respect to xil, it becomes zl. But where the summation goes, as we talked about it in the previous session, this summation, you can open it in this way. xi1, it becomes, its summation is over L, right? So you can write xi1 z1 plus xi2 z2 until plus xl, yeah, sorry, xln zn. I think I should write it in a cleaner way. Let it be m neurons, doesn't matter, zn. Okay, now assume I say take derivative of ai with respect to xi2. What is it? So this is the whole ai, right? This term is constant with respect to xi2, becomes 0. All of them are constant with respect to xi2 except this one. So its derivative becomes z2. Now replace 2 with L. So whenever we say derivative of ai with respect to xil, we mean with respect to xil with a specific L. Okay, therefore summation goes away. We see that a lot in machine learning. Okay, so summation goes away, zl becomes the derivative. Here it is. And let's denote with, I define derivative of E with respect to ai to be delta I. And therefore I replace this with delta I, right? Now, do you agree that delta I can be computed very easily in the last layer? What is delta I? What is delta I? It's derivative of error with respect to ai. What was ai before activation function? In the last layer, if we don't have any activation function, assume we don't have any activation function. Then what is derivative of E with respect to AI? It depends on the cost. Which loss are we using? If it is mean squared error, so it's exactly, you need to take derivative of that loss function. What if in the last layer we have an activation function? Then this can be found usually using a simple chain rule. It will be derivative of E with respect to Zi times derivative of Zi with respect to AI. Derivative of E with respect to Zi in the last layer is just the derivative of the cost function, right? Because Zi is fed to the loss function. Derivative of Zi with respect to AI is a derivative of activation function, right? Again, in the last layer, I have AI, Zi, assume I'm in the last layer, and this is cost. Okay. Two cases. Sometimes I don't use any activation function in the last layer. Okay. Then this is the case. Sometimes I use activation function in the last layer. And this is the case. Now let's consider the easier case, which is this. I don't use any activation function in the last layer. Derivative of E with respect to AI, which is delta I, is exactly the gradient of cost prime. It's derivative of cost, right? This case now, harder. Delta I, which is derivative of E with respect to AI, you can write it as derivative of E with respect to Zi, chain rule, times derivative of Zi with respect to AI. What is derivative of E with respect to Zi? Again, derivative of cost prime. What is derivative of Zi with respect to AI? It's exactly activation function prime. It's derivative of activation function. Why? Zi equals sigma I AI. Derivative of Zi with respect to AI becomes sigma I prime. Clear? Okay. So for the last layer, delta I is easily computed. And in the other layers, in the hidden layers. So if a layer is not in the last layer, we can call it hidden layer. Okay. In the hidden layers, if I is one of the hidden layers, then delta I can be computed again by chain rule. How? Derivative of E with respect to AI, which is delta I, we can write it in this way. Let me clean this. Derivative of E with respect to AI. You can write it as summation of derivative of E with respect to AJ, which is this, the next layer, times derivative of AJ with respect to AI. So this is E, derivative of E with respect to AJ, then derivative of AJ with respect to AI. But why do I have this summation over J? Because in the next layer, which is this, layer I is this. This is the next layer, right? There is not only one neuron. There are a lot of neurons. All of them are connected to this ith neuron. So I have these. I should sum over all of them, right? All of them have impact on this, right? Therefore, I have summation over J, which is summation over the neurons in this layer. Now, what is derivative of E with respect to AJ? Derivative of E with respect to AJ. By definition, it is delta J. Delta I was the derivative of E with respect to AI. Therefore, derivative of E with respect to AJ is delta J, right? And I also write the derivative of AJ with respect to AI. I repeat it here. As you see, delta I depends on delta J. Delta I is in this layer. Delta J is in this layer. Therefore, every layer depends on its next layer. Okay? So now let's calculate derivative of AJ with respect to AI. It's here. So you again chain rules. As you see, I'm using multiple chain rules inside of each other. Therefore, I'm having nested chain rule. Okay. So derivative of aj with respect to ai. Let me clean this figure. And also this. So derivative of aj, it's here, with respect to zi times derivative of zi with respect to ai. So this and then this. This is chain rule. Derivative of aj with respect to ai, I can write it as derivative of aj with respect to zi, and then derivative of zi with respect to ai. Here. Okay, it makes sense. And now, derivative of aj with respect to, we know that aj is summation of xji zi, right? According to what we had here. For all neurons, we have such equation, right? So for aj, it's summation of xji zi, summation is over I. Summation is over I, because all of these neurons are connected to this. And if you open this summation again, as before, what do we have? xi1, z1, xi2, z2, etc. Therefore, derivative of aj with respect to zi for a specific I becomes, this is j, sorry, xji. Exactly as we have put here. Correct? And derivative of zi with respect to ai. What is that? Derivative of zi with respect to ai. It's sigma prime ai or sigma I prime ai. Why? Because of this. Zi is sigma I ai. It's here. So I replace this with this. Okay. Now I put this back in the equation 11. So I put equation 12 back in the equation 11. I substitute this derivative with what I found here. Okay. What happens? Delta I becomes, if I put this, what happens? Sigma over j, delta j, x ji, sigma I prime or sigma prime, doesn't matter, ai. When I say sigma prime, I don't use subscript I for sigma. I mean, I'm using the same activation function for all neurons, okay? But if I say sigma I, it means that the activation function for the ith neuron. Doesn't matter. So then what happens? Do you agree that this sigma I prime ai doesn't depend on j? So I can bring it out of the summation, as I have done it here. Okay. Then I will end up with this times summation delta j x j I. Summation is over j. I mean, summation is over the neurons in this layer. Okay. So delta I is found. And delta j, so xji is it has some value, because as I said, we are using gradient descent. Initially, we have some random solutions because randomly we choose some weights, right? Then this means that xji, this means that the xji, the weight in the previous iteration of gradient descent. Okay. If it is in the first iteration, it's just the initial random xji which we got. Okay. If it's in the second iteration, it's xji from the first iteration. All right. So the previous xji. So xji is known. Sigma prime ai, which is the derivative of sigma function, but we feed ai to it as input. It's also known because you feed some input to the network, so all of the AIs you can get, right? You can calculate. It's easy. So you have AIs. Delta J, you also know that. Why? Because you're backpropagating the error. You know that delta J in the last layer, also one to the, you are coming back. So you always know the delta of the next layer. So all of them are known. So delta I is also known. Right? Now, This is what we found. I'm repeating it here. Putting this in equation 10. What was equation 10? It was this. Let me go back for you to recall. This was equation 10. It had delta I in it. So I've substitute delta I, which I found in this equation. Okay. This is what I found for delta I. So I put it here. Then what happens? ZL, this is ZL, and this is delta I. Right? So back propagation, and this is the gradient, right? This derivative is gradient, which we are going to use in gradient descent, right? Back propagation uses the gradient in equation 13 for updating the weight XIL for all I and L. What do I mean by for all I and L? For all neurons in this I layer and for all neurons in this L layer. So it means that for all weights in these, between these two, and you do it for all of the layers. So it means that for all layers, for all weights. And this is simply a step of gradient descent, where K denotes the iteration index, right? This eta K is the learning rate, also called step size, whatever you call it, for the K's iteration. You can set it to be fixed, or you can gradually decrease it. Why do we gradually decrease it? Because initially, we assume that we are very far away from the solution. But the closer we get to the actual solution, we don't want to oscillate around that. So we gradually reduce eta. Okay? And as you saw, it was very simple. Backpropagation was very simple. I have seen several explanations for backpropagation. This is the simplest one. And this was taught by Professor Ali Qudsi. Okay? I adopted his explanation. This is the simplest one. So this tunes the weights from the last layer to the first layer for every iteration of optimization. Okay? Therefore, backpropagation proposed in 1986 is actually gradient descent with chain rule in derivatives because of having layers of parameters. As we have layers depend on each other. Therefore, we have to use chain rule. If it was if we didn't have any layers, then it would be just simple gradient descent. Many of the machine learning algorithms use only simple gradient descent. They don't have any chain rule, right? So it is the most well-known optimization method used for training neural networks. Note that backpropagation is not the only algorithm for training neural networks. There's some meta-heuristic optimization algorithms are also used for example, they have used genetic algorithms for learning weights in the neural network. You should do some kind of optimization to learn the weights, right? The simplest one is gradient descent and chain rule, and the most successful one, at least so far, right? Some other algorithms have been proposed. Recently, Hinton proposed forward algorithm. I'm not sure how successful it is, but these are some algorithms. So this is the most well-known. And I think you can figure out, you can imagine how exciting it was for them. How did they come up with this algorithm? They said, okay, I have some layers of parameters, and I have some cost function. How can I learn the weights? This is their thought in 1986, right? At that time, 1980s to 1986, they said, okay, so we have to do optimization, because as you know, machine learning is all optimization plus some other things such as probability, linear algebra, and these things. You have to use optimization. Okay, the simplest optimization at that time, first order optimization, gradient this. But there is a problem. Weights depend on each other. So chain rule. This is how they ended up with backpropagation algorithm, and it worked. Okay. Stochastic gradient methods. Assume we have a data set of n data points. Okay, AI. In RD, I goes from 1 to n. Okay. Here, I'm denoting data points by AI. You can denote it by X if Why don't I use X here? Because I don't want it to be confused with the X's that I use for weights, okay? So under labels, Li, which are, assume they are scalar labels, okay? I goes from 1 to n. Let the cost function f be decomposed into summation of n terms. So we are assuming that we are using a cost function which is decomposable to n terms, okay? f1 to fn. Then some well-known examples of this cost function are these. For example, least squares error like this, fi, you can consider it as this, and absolute error, we can consider it as this. So you are, the x here is the weight, x here is the weight, ai is the data, and li is the label. So you are saying that this is saying that let the last layer of neural network be x, for example, and A transpose X means that you apply you apply the input of the last layer of neural network, which is AI. Here, don't be confused. Here, I'm assuming in this notation, I'm assuming this is one layer neural network, but you can have it for multi-layer neural networks. Doesn't matter. I'm just using these to show you how we can have decomposable cost functions. Okay, so here we are saying that let it be output of neural network. If it's one layer, then it becomes AI transpose X. If it's multiple layers, then it becomes some functional AI. Okay, minus Li. So I want the output to be as close as possible to Li, but I square it. So it's a least squared error, and this is a squared, therefore squares. Least becomes because I'm minimizing this cost function. Absolute error is like this. So you can have various ways. Hinge loss, such as this. Whenever in machine learning, we have the loss function is maximum of 0 and something. This is called hinge loss. Okay. So maximum of 0 and the output of neural network is hinge loss. And why do we do that? What's the philosophy behind that? It's saying that I don't care if the cost becomes negative. Okay. The only thing which I need to penalize is when it is positive. Okay. When it becomes negative, saturate it to be 0. Okay. That's one thing. And logistic loss, you can bring this inside the logistic function or sigmoid function. Okay. So these are some examples for what I mean by decomposable. But the important thing is that I use summation of. So I use summation of fix, right? I goes from 1 to n, where x is the optimization variable. In neural network, x is the weights. Okay. So I'm taking average. In this case, the full gradient. Consider this optimization problem. What is the full gradient? It's exactly this. So the gradient of this cost function, derivative is linear, a linear operator. Do you agree? So it passes through the summation. So we'll have 1 over n summation derivative of fi rather than fi. Okay. This is the whole gradient. Okay. And why do I call it full gradient? Because later in a few slides, we're gonna use not all of them. That's a subset of them. Okay. When you are using all of the f1 to fn, it's full gradient. Okay. And delta x in the gradient descent then becomes minus eta gradient of f, right? This is the update in the gradient descent. Do you agree? Xk plus 1 is xk plus delta x, delta xk. This is delta xk, right? Minus eta gradient of f. Then it becomes this. So I'm substituting this gradient of f here, right? If you put equation 15 in this, it becomes this. Okay. This is what gradient descent uses for updating the solution at every iteration. This is exactly what gradient descent is doing. Gradient descent uses a full gradient. This is called the gradient descent algorithm. Okay, it uses the whole gradient. Whatever you give to it as a cost function, it takes derivative and uses that. This is gradient. Now let's talk about a stochastic gradient descent. What is its difference? We see. So this was the full gradient, right? Calculation of this full gradient is time consuming. Assume n is large. It's time consuming. If n is 1 million, I need to take derivative of f1 to f1 million and then sum them. So a loop, and inside every loop I need to take derivative. Okay.
In case of like a normal gradient descent, we like go through all the training examples and sort of then update.
Yeah, exactly.
Not after like each example.
Yes, gradient descent uses all of the data points. So
we update the weights after going through all the training points and like then update.
Yes. Exactly. In gradient descent, we go over all. So n is, you can see it as a number of training points. Okay, training data points. So when we are saying the full gradient, it means that calculate the gradient for all of the data points, and that is time consuming. Okay, this is what gradient descent does, and that's why usually gradient descent itself is not used in backpropagation. We use a modified version, which is a stochastic gradient descent. We'll see that. Okay, so it's time consuming and it is inefficient for large values of n. As I said, n might be 1 million data points you might have. Okay, so especially as it needs to be recalculated at every iteration. So we use a stochastic gradient descent, or SGD in short, also called a stochastic gradient method. Okay, what does it do? It approximates gradient descent, approximates it stochastically, and when I say stochastically, I mean randomly. Okay, and samples or bootstraps one of the points at every iteration. I tell you what bootstrap is. Bootstrapping in statistics means sampling, as far as I remember, with replacement. Okay, whenever you take something, you have a set of data points, you randomly take one of them, then you put it back, so you will have the set again, then randomly take another one. This is called bootstrapping. Okay, either bootstrapping or simple random sampling, which is sampling without replacement. Doesn't matter. Simple random sampling is sampling without replacement. Bootstrapping is sampling with replacement. Each of them doesn't matter. You can sample or bootstrap one of the points at every iteration for updating the solution. So as you see, now I'm using gradient of Fix rather than full gradient. So I have a set of data points. Full gradient uses all of them for every iteration of gradient descent. A stochastic gradient descent says, no, at every iteration, I just sample one of them. Okay. Then, rather than, this is gradient descent, but this equation 16 is the stochastic gradient descent. You can compare them. The difference is in the gradient. Okay, the idea, as you see, it is approximating. Of course, it's not exactly, they are not the same. It is approximating by one gradient rather than the full gradient. Okay, this and hence they can call it, if people, for the people who are purely in optimization mathematics, they don't like to call it a stochastic gradient descent because it's not gradient descent anymore. Gradient descent, the descent direction is the opposite of ascent direction. It's not descent anymore. It approximates that. Therefore, they call it stochastic gradient method. Okay, that is the reason. So the idea of a stochastic approximation, stochastic, as I said, it's like random. Don't be afraid of this name. It's just random. Okay, and not random is deterministic. Okay? A stochastic approximation was first proposed in 1951. And see how old it is. It was first used for machine learning in 1998. Okay, references 8 and 9. As equation 16 states, SGD, stochastic gradient descent, often uses an adaptive step size which changes in every iteration. This. In gradient descent, we can also do that. Okay, so the step size can be decreasing because in initial iterations where we are far away from the optimal solution, the step size can be large. However, it should be small in the last iterations, which is supposed to be close to the optimal solution. When we are close to the optimal solution, we don't want to oscillate around the optimal solution. That's why we decrease that. And there are several ways to decrease it. Various ways. Okay. This last one is not decreasing, it's fixed step size. But these are decreasing. So K is the number of iterations, these are decreasing functions. And you should note that no matter whether you use decreasing or adaptive, also called adaptive learning rate, or fixed learning rate, initially it should be small enough. If it's too large, it will oscillate a lot and it doesn't work. It should be small enough. Okay. So we'll assume you are coming down of a mountain. You don't want to jump from one mountain to another mountain. Doesn't make sense. You need to have steps over the mountain or the same mountain, right? Okay, that's one thing. We will now analyze gradient descent, stochastic gradient descent, and we'll also introduce mini batch gradient descent. And I think it's very exciting. It's analysis. We'll see. Okay, so convergence rate of gradient descent is this. Consider a convex. So these are the assumptions we need for this convergence rate. What do I mean by convergence rate, by the way? It means this. So it means assume that optimal solution is f star, okay? And I'm in the t+1 iteration, okay? T here denotes the iteration index. Then it means that how fast I move toward f star, okay? How fast. The better convergence rate, the faster the algorithm it is, okay? So consider a convex function, differentiable function, so it's a smooth f, okay? With domain f, domain D, so where x should belong to, whose gradient is L smooth. What was L smoothness? Lipschitz continuity. I talked about it in the last session, but let me briefly say it again. So when we say a function is L smooth, L here is a parameter. It's a scalar, okay? For example, it can be 1.2 or something. It means that the slope of the function is upper bounded by L. Okay, it's the upper bound of the slope is L. Why is it important? So what do I mean by slope? For example, this is the function. This is the slope at this point. At this point, this is the slope. At this point, this is the slope. And this is in a 1D function. If it is multiple, then we will have slopes of hyperplanes, okay? Tangent on the function. So why is it important? Why is L smoothness important in optimization? Almost in all proofs of optimization, you will see L smoothness because consider this function. Its a slope here goes to infinity, so it's not L smooth, and it's very assume I want to maximize it. It's hard to find its maximization. It's very hard. So the more the L, the harder the optimization. But consider this function. It's a smooth. Its slope is not huge. Easily I can maximize it. Right? Easily I can maximize. So L smoothness shows how hard it is to optimize. Okay. Now here, because if you want to see the proofs of this, you will see that we need to assume that the gradient of f is L smooth. Okay, not f. The gradient of f is L smooth. The gradient of f, its slope is upper bounded by L. Okay, let f star be the minimum of cost function. Okay, because I want to minimize, and x star be the minimizer. What do I mean? This is x star. This is f of x star, which I denote by f star. Okay, so starting from the initial point x0, after t iterations of the optimization algorithm, we'll have the following. This is the convergence rate. So to this distance, by distance, I don't mean the distance of x's, I mean the distances of cost values. Okay, cost values, the distance of So of course, f minus f star is, we know that, less than or equal to f of x t plus 1. So this is always greater than or equal to 0, because f star is a minimum cost. Okay, so this is 2 times L squared L2 norm of x0 minus x star. This is the distance of x's, but the distance of x star and the initial point. Okay, not the point at this iteration. x0 and x star. 2L, and we have t plus 1 here. Okay, L, does it matter which iteration we are? No. So it's a constant. x0, it doesn't matter which iteration we are. X star doesn't matter. Only in the denominator we have t. Okay, so it's all in the order of 1 over t. Or order of 1 over t plus 1, which is order of 1 over t. Okay, this is big O notation. So in time complexity and in complexity. Okay, this is in time complexity. So it means that our convergence rate in gradient descent is 1 over t, in the order of 1 over t. Now, convergence rate of a stochastic gradient descent. Let's see that. Consider a function. Now the function is decomposable to n functions, summation of n functions, which is bounded below. What do I mean by bounded below? Doesn't go to minus infinity. Okay, it is bounded below, and each fi is differentiable, smooth. Okay, let the domain of function f be d. Okay, its gradient also be L smooth. That's fine. Assume we are having another assumption. Assume expectation, conditional expectation of squared L2 normal of gradient of fi conditioned on xk is less than or equal to beta squared. Doesn't matter. This is just some assumption that they have used to prove these convergence criteria, where beta is a constant. Doesn't matter. Assume also we have this. Oh, yeah, I think I've repeated this sentence twice. Doesn't matter. Okay, depending on the step size, as I said, we can have fixed step size or decreasing the step size. We have different convergence rates. Interesting, right? Okay, so if delta is if eta is 1 over tau, okay, or 1 over t, whatever you call it, doesn't matter. This is the convergence rate. It's big O 1 over log of t. Okay. If eta is 1 over, is decreasing in this way, 1 over square root of t or tau, its convergence rate is big O log of t over square root of t. If eta is fixed, its convergence rate is big O of 1 over t plus eta, and you will see how interesting these are. We are gonna analyze them. Okay, where tau or t denotes the iteration index. If the function fi's are mu strongly convex, so what do I mean by strongly convex? This is a convex function, but it's not strongly convex. This is strongly convex. So when I choose these 2 points and connect them, they are still above the function, but here they are exactly touching some part of the function. Although it's convex, but it's not strongly convex. For the formal definition of strongly convex, see my optimization course, okay, preliminaries. But doesn't matter. Mu is also a parameter in how strong it is in terms of strongly convex. If that's the case, then the convergence rate of SGD is this. If eta is 1 over mu tau, its convergence is 1 over t. If mu tau is if the learning rate is fixed, then its convergence rate is 1 minus mu over L to the power of t plus eta. You shouldn't memorize this. You should analyze it. Okay, we are gonna you don't need to memorize it. Don't be scared of this. So we are gonna understand them. Okay. Recall equations 21 and 23. So what do we have? We said that for what was 21? This. And this. 23 is this. Okay. We are considering the fixed step size for now. Okay. Because I want to analyze it. For fixed step size, for convex or non-convex, the stochastic gradient descent is convergence rate is 1 over t plus eta. In strongly convex, it is 1 minus mu over L t plus eta. Okay, these equations show that with a fixed step size, eta, SGD converges sublinearly for a non-convex function. It's sublinearly, 1 over t. Linearly, this is linearly. 1 over t is sublinearly, okay? It's sublinearly for a non-convex function and exponentially for a strongly convex function. T here is in the exponential, is in power, right? What does it mean? If the function is easy to optimize, it's strongly convex, SGD is much faster. Much faster. It's exponential. But if it's either non-convex, it's not convex, or convex but not strongly convex, it's slower to converge. Okay. Now, some other interesting insights. However, in the late iterations, it stagnates to a neighborhood around the optimal point and never reaches that. Why? Let's discuss it. Limit t to infinity. For infinite number of iterations, after infinite number of iterations of SGD, what happens? This 1 over t becomes 0, goes to 0. So this becomes the distance. Do you remember the distance of cost? This was the distance of cost. All of them in the left-hand side, we had the distance of current cost from the optimal cost, right? This becomes O eta. Oh my goodness. It means that it never becomes 0. This distance never becomes 0. Always eta, even after infinite number of iterations. This is the flaw of the stochastic gradient descent. Okay. Now see gradient descent. Equation 18 was the convergence rate of gradient descent. After infinite number of iterations, it becomes 0. If you use full gradient, at the end, you will reach the optimal solution, assuming it's convex, okay? But even if it is convex, if you use a stochastic gradient descent, you never reach that. At the end, you will oscillate around that. By what step size? By eta. But by its cost will be eta. For example, assume, what do I mean by that? Assume this is the optimal f star. As you are not using a full gradient and you're just sampling one point at a time, in very late iterations, for example, you are here, then you jump here, then you jump back here, and this distance is eta. Okay. And if you had chosen the fixed step learning rate to be small, then it would be negligible. Do you get it? Always there's trade-off in machine learning, in math and in life, in all of them. Okay? Trade-off. Using full gradient is time-consuming, hard. But if you wanted to improve it every iteration in terms of time complexity, then at the end it will pay off. You will not reach to the optimal solution. Did you get it? How interesting it is. How interesting. Okay. So the convergence, the advantage of SGD over gradient descent is that its every iteration is much faster than every iteration of gradient descent, of course, because we are just sampling one point rather than have the full gradient. Because of less computations for gradient, this faster pacing of every iteration shows off more when n is huge. Of course, when n is huge, it's too hard to compute the full gradient. In summary, SGD has fast convergence to a low accurate optimal solution. Right? It's fast every iteration, but at the end it's low accurate. It is noteworthy that the full gradient is not available in SGD to use for checking convergence. Do you remember what one of the convergence criteria? What do I mean by convergence criteria? When to stop the optimization? Okay, one of them we were using for L2 norm of gradient. Do you remember? If it is less than some epsilon, stop. But now in SGD, we don't have the full gradient. So we need to change those convergence criteria. One can use other criteria or merely check the norm of gradient for the sampled point, right? Because you have gradient of Fi only rather than gradient of, okay. SGD can be used with line search methods too. Recall the previous sessions, which we talked about line search. So we can use that, okay. We can also use momentum term, okay. Now that we talked about gradient descent and the stochastic gradient descent, let's talk about mini batch stochastic gradient descent, okay. Gradient descent uses the entire gradient descent, uses the entire n data points. SGD uses one randomly sampled point at every iteration. So these are the two extreme cases. Now let's have a middle case scenario, okay. For large data sets, gradient descent is very slow because of full gradient calculation and interactable, of course, in every iteration, while SGD will need a significant number of iterations to roughly cover all data, right? Assume you have a huge number of data points. If SGD wants to cover all of the data points, we need a lot of iterations, right? To see all of the data points. Besides, SGD has low accuracy in convergence to the optimal solution, right? So let's have a middle case scenario. We can have a middle case where we use a batch of B randomly sampled points at every iteration. Rather than one random point, let's use B of them. This method is named mini batch SGD or hybrid deterministic stochastic gradient. Okay. Method. This batch-wise approach is wise for large data sets. Of course, it's too large. Gradient descent doesn't make sense. Full gradient calculation is very hard. Also, a stochastic gradient descent has its own flaws. So let's use mini batch stochastic gradient descent. Okay. Usually, before a start of optimization, the n data points are randomly divided into some batches of size B. Therefore, how many batches will we have? N over B. This is floor because I want it to be integer. Okay. This is equivalent to simple random sampling for sampling points into batches without replacement. Okay. You can also see it. You can also see it as cluster sampling. There are several algorithms for sampling. You can take a look at my tutorial paper, Sampling Algorithms from Survey Sampling to Monte Carlo Methods, Tutorial and Literature Review. This is its title, okay? I have explained different ways for sampling, but one of them is simple random sampling. One of them is stratified sampling. One of them is cluster sampling. There are other interesting algorithms such as a snowball sampling, something like that. You can take a look at them. So you can see it as cluster sampling because you have some clusters. So what is the difference between these three: simple random sampling, stratified sampling, and cluster sampling? Simple random sampling, you randomly sample one point, but stratified sampling, it says let's have several clusters or strata. Each cluster is also called a stratum, doesn't matter. It's plural is a strata. So you go and in each stratum, as far as I remember, you do simple random sampling. So it becomes a bit fair because you go and in each strata, you take some of them. For example, what does it mean? For example, you want to do, what was the word in English? What was Sarsham in English? I don't remember it. Okay. So you want to take the statistics of the country. What are the ages and what is this? What? What? Demographics. I don't know. Do you want to find out the statistics about the population? Okay. You can go to each house and sample from that house. What? Census, I think, yes, census. Okay, so you can go, and this is a stratified sample. Cluster sampling says no. Let's sample clusters. So divide your data into clusters and then do simple random sampling in the cluster level. Okay, so as you see, there are some differences between these sampling algorithms. So you can see it as cluster sampling too, but it doesn't matter. What were we saying? So we have some batches and we sample the batches. Okay, this is equivalent to simple random sampling, as I said. Okay, we denote the data set by D, where the size of D is n. Okay, and the ith batch is bi. Okay, and every batch we assume that they have the same size, b. Okay, the batches are disjoint. This is important. They don't have any overlap. Usually this is what we do. This is not a must, but this is what we do usually. So their union becomes the whole D, but each of them, their intersection is empty set. Okay, for all ij, indexing the batches. Okay, another less used approach for making batches is to sample points for a batch during optimization. Okay, so either we do it before start of optimization, before start of backpropagation, or during that, doesn't matter. Okay, this is equivalent to bootstrapping for sampling points into batches with replacement. Okay, in this case, the batches are not disjoint anymore. So again, when we do it during optimization, we can sample with replacement. So we sample one of the batches, we get one of the batches. That's why I called it bootstrapping. And then they might not be disjoint. So for example, I have a bunch of data points, and then I take several of them as a batch, okay, during optimization. So we have different ways to get to do mini batch stochastic gradient descent. I think the simplest one is that before start of optimization, you just divide your data to several batches. Okay. Now let's talk about epoch. The definition in mini batch stochastic gradient descent, when all batches n over b batches of data are used for optimization once an epoch is completed. So epoch means that we have gone over all data once. We have used all of the batches once. In the next epoch, we go over the batches again. Okay, we can shuffle the batches too in every epoch. We don't need to take the same order of batches in the epochs. In this epoch, in the first epoch, I might take batch 1, then batch 7, then batch 2. In epoch 2, I might take batch 10, then batch 11, then batch 1. Right? Something like that. But we need to go over all batches to have an epoch completed. After completion of an epoch, the next epoch is started, and epochs are repeated until convergence of optimization. We can use different convergence criteria, which we discussed. In mini batch SGD, if the case iteration of optimization is using the K prime F batch, the optimal solution is this. This is a step of mini batch stochastic gradient descent. As you see, rather than full gradient, what was full gradient? 1 over n summation over from I goes to 1 to n gradient of fi. But rather than 1 over n, I have 1 over b summation over the batch, the samples of the batch. Okay, so I'm taking the average from the batch rather than from the whole data. Okay, and this is we can drop this constant too. Constant scales are not important for optimization, because if you have a scale times some optimization variable, then if you drop that, for example, what do I mean? For example, 1 over b, the cost, then you will find some optimization, optimal optimization variable. If you drop that, then for example, you will get b times that optimization variable, right? So the scale is not important. Mini batch stochastic gradient descent is used significantly in machine learning, especially in neural networks. And it's interesting that when in neural networks, whenever they say SGD, they usually mean mini batch SGD. So sometimes in the literature, they are used interchangeably. Okay, when they say SGD, they mean mini batch SGD. Because of dividing data into batches, mini batch SGD can be solved on parallel servers, right? We can do that too. So it can be parallelized. And that's why neural networks can use GPU, right? They can use CUDA in GPU as a distributed optimization method. For more information on distributed optimization algorithms, you can see my optimization course. One of the well-known and state-of-the-art distributed optimization methods is alternating direction method of multipliers, or ADMM. That's not related to neural networks, but that's a cool algorithm you can take a look at. Okay. Okay, convergence rates for mini batch SGD, consider a function this, which is bounded below. So this is a decomposable function bounded below. Again, each fi is differentiable. The domain is D, gradient is L smooth. Assume this is the learning rate is fixed. The batch-wise gradient is an approximation. This is an important. Batch-wise gradient is an approximation to the full gradient with some error. So this is the gradient of the batch. This is the full gradient. Okay, so you can write it as the batch gradient of batch is the full gradient plus some error. Do you agree? In the tth iteration. So the error at every iteration is different, right? Because at every iteration we are taking different batches. And the convergence rate of mini batch SGD for non-convex and convex functions are this. Is this O, big O of 1 over T plus square L2 norm of the error, where T is the iteration index. And if the function is mu strongly convex, then this is the convergence rate. O of 1 minus mu over L to the power of T plus a squared L2 norm of ET. And we are going to analyze this too. So therefore, the convergence rate of mini batch gets closer to that of gradient descent, which is O. Do you remember? This was the convergence rate of gradient descent, right? If the batch size increases, why? Why is that the case? In this equation, if you increase the batch size, this gradient of batch becomes closer to the full gradient because you're making the batch bigger and bigger. So it is approximating the full gradient better. Then the error becomes lower. Then these two, no, this especially, this limits become, in limit becomes O over 1 plus O of 1 over T, because this E T goes to 0, right? And now you see the trade-off. The bigger batches, the more accurate, but the harder to optimize at every iteration, right? This is a trade-off. Okay. If we sample, now another analysis of this. If we sample the batches without replacement, that is sampling batches by simple random sampling. Okay, simple random sampling before the start of optimization. Okay, or with replacement, which is bootstrapping during optimization. These are the expected errors. So if it is without replacement, equation 30. If it is with replacement, equation 31. For proofs, you can see my tutorial paper, proposition 3, tutorial paper of sampling algorithms. Okay, now let's analyze them. Let's analyze. Okay, and what is sigma squared? Is the variance of whole data set. Okay, according to equations 30 and 31, the accuracy of SGD by sampling without and with replacement increases by B going to N or B going to infinite. Let me explain it. So consider equation 30. What is it? Expectation of error for sampling without replacement. And it means that when does it become 0? If this parenthesis becomes 0. It means that when B over N is 1, it means that when B is N, increase B to become the whole data set size. So one batch is the whole data. So of course, error becomes 0. Okay. When does the without replacement? Now with replacement, equation 31, with replacement. When does it become 0? B should go to infinity. So this goes to 0. It's obvious because you're doing it with replacement. sometimes you might take the same batch again and again. So B should become very large, goes to infinity. However, this increase makes every iteration slower. So there is a trade-off, as I said. Now, let's talk about adaptive learning rate. Okay. From now on, I'm gonna derive and talk about ADAM. So there are two optimizers, famous optimizers in neural networks, SGD, which we talked about, which they mean mini batch SGD, and ADAM. Okay. So now let's talk about ADAM, starting from this slide. So we can adapt the learning rate in a stochastic gradient methods. Okay. Three most well-known methods for adapting the learning rate. What was the learning rate? The eta. Do you remember? Eta was a learning rate. There are three methods at least. AdaGrad, RMSProp, and ADAM. Okay. So let's talk about them. Let's first talk about AdaGrad, short for adaptive gradient. It was proposed in 2011. As you see, we are closer to the state of the art. 2011 in reference 12. It updates the solution iteratively as this, equation 32. Let's take a look at that. So the only difference from gradient descent is this G inverse. If you drop the G inverse, it becomes a stochastic gradient descent. The only difference of this and a stochastic gradient descent is G inverse, right? Okay, let's see. G is a D by D diagonal matrix. So it's diagonal and it is D by D. What is D? The dimensionality of data, X. Okay. In neural network, D is the dimensionality of weight. Okay. So its jth element is this. As I said, it's diagonal. So its jth element is equation 33. Let's see that. So this epsilon in this equation here is for stability. Why? Why do I add this? Because I have G inverse. Okay. One technique in linear algebra, one hack you can see, hack technique is, or one ad hoc technique is strengthening the main diagonal of a matrix. Why? If your matrix is singular or it's not full rank, you can't take inverse, right? It will throw error. For it to become full rank and non-singular and invertible, you can simply strengthen its main diagonal, okay, by a positive number. So it makes it full rank. However, you should note that when you do that, you become less accurate because it's not the original matrix anymore. So you don't want to add a huge number. If you add it, then the whole accuracy goes away. But it shouldn't be very small. If it's too small, then it might still remain singular. So again, it's trade-off. Some small value is small enough to make it full rank. Okay, it's a hack used a lot in machine learning. Okay, so that's why we use that because we want to take inverse. We add epsilon, making G full rank, and I tau is a randomly sampled point from 1 to the n at iteration tau. Okay, I tau, we are, as I said, in a stochastic gradient descent, we sample one of the points, right? Let the index of that sampled point be I tau. Here it is, Fi tau, right? Fi tau. And this gradient of Fi tau, J, gradient of J, is a partial derivative of Fi tau with respect to its jth element. Note that Fi tau is d-dimensional. Why is Fi tau d-dimensional? F itself is a scalar function. Its output is scalar. X is d-dimensional. Derivative of a scalar with respect to a d-dimensional vector is a d-dimensional vector. So recall preliminaries. So a gradient of I tau. So Fi tau. It's derivative. I should say. Note that gradient of Fi tau is d-dimensional. I apologize. So gradient is d-dimensional, let it be take the jth element of that gradient. Then it becomes gradient of j fi tau. Did you get what I mean? So gradient of fi tau is d-dimensional. The jth element is this. Okay. Now we have a squared here. We also sum over t from tau from 0 to k. Okay. So and what is k? The current iteration index, right? And so we are summing over all of the iterations so far, right? Okay. Now putting equation 33 inside equation 32 can simplify the AdaGrad in this way. You can write it in this as equation 34. What is this? So this is already from here, which was from the stochastic gradient descent, and this is the G inverse. Okay. Note that, see the difference between equation 32 and 34. In equation 32, this is for the whole vector. In equation 34, this is for the jth element of the vector. Okay. That's why I'm writing G inverse element wise here. Okay. So far clear? And as it is, why is the jth element of G this? Can you tell me? G is a diagonal matrix. What is the inverse of diagonal matrix in linear algebra? It's the inverse of its diagonal. Okay. The inverse of a diagonal matrix is still a diagonal matrix, but its diagonal elements are inverse, are reciprocal. Okay. So that's why I have this term goes to the denominator. Exactly what we have. Okay. And this eta also is here. So far clear? Note that equation 34 is elements wise for the jth element of x. Okay. And now let's analyze it. Let's see what it is doing. AdaGrad keeps a history of the sampled points. Do you remember? Because tau goes from 0 to k, and I have f of I tau here. So history of the sample points, and it takes derivative for them to use. Okay. During the iteration so far. Why? Because tau goes from 0 to k. If a dimension has changed significantly, it dampens the learning rate for that dimension. Why? Yeah, yes, but let me say what you said in other words. That first, mathematically, why is it the case? So the gradients, the jth gradients, as you see in the jth dimension of gradient is in the denominator. Do you agree? Okay. So when it is large, this becomes a small. This square root is in the denominator times eta. So it is a scaling the learning rate eta. Okay. It is a scaling the learning rate eta. If you don't have this denominator, it becomes a stochastic gradient descent. But it is a scaling the eta in the stochastic gradient descent. Okay. When this gradient for the jth dimension is very large, this denominator blows up. Therefore, the learning rate becomes very small. Do you agree? A small number times the eta. So that's the reason. And why are we doing that? Because we want to have a fair contribution of all dimensions. Assume you are using a stochastic gradient descent, and maybe one of the dimensions becomes dominant. It dominates the optimization. It always, in every iteration, we are moving in that direction, in that dimension, most often. But we are not giving any chance to other dimensions. Let's make it fair. Okay. So in this way, when it is eating all of the food of optimization, we dampen it. We say we don't want to move toward you anymore. Let's give chance to other dimensions. Okay. So that's the reason. Hence, it gives more weight for changing the dimensions which have not changed noticeably. In this way, all dimensions will have a fair chance to change. Okay, so it's an improvement. And this is the analysis. Okay. Fairness is important. This was AdaGrad. Now, root mean square propagation, in short, RMSProp. This is also important in machine learning, RMSProp. It was first proposed in 2012. So AdaGrad was in 2011, RMSProp was in 2012. And it was unpublished. Why? It was in a lecture of Hinton, a slide deck of Hinton, when he was teaching in University of Toronto. Interesting. Okay, it is unpublished. But it became an important method in machine learning. So it is an improved version of RProp. This is another algorithm. RProp, short for resilient backpropagation, proposed in 1992. Okay, reference 14, which uses the sign of gradient in optimization. This algorithm, this RProp, it uses the sign of gradient in optimization. I don't go in detail of that algorithm. Let's talk about RMSProp. Okay, what does it do? Do you remember momentum? We talked about it in the previous session. Okay, momentum was saying that delta x has a log of previous delta x, and this was exactly the momentum, equation 8. So delta x of this iteration has a log of the previous iteration update, and this is the update in the gradient descent. So I'm adding this. If I don't have this, if I set alpha to 0, this becomes the gradient descent without momentum. Why am I doing that? I don't want to oscillate a lot. When I'm having a log of previous delta x, it means that I want to be similar to that. I want to be similar to the previous delta x, so I don't oscillate much. Okay. Now it updates a scalar variable. So what is inspired by this? Our RMSProp does that. Equation 35 is RMSProp. So equation 35 and 36 together. So RMSProp defines a new variable named v, and it is a scalar. Okay. V is also updated at every iteration. V of k plus 1 is gamma vk plus 1 minus gamma squared L2 normal gradient of fi xik. So gradient for the ith point, take its squared L2 norm and put it in this update, and you update v. Gamma is some scalar between 0 and 1. It's called forgetting factor. Okay, and it's usually set to 0.9, for example. Okay, then it uses this v to weight the learning rate. As I said, all of these algorithms, in these 3 algorithms that I'm talking, they weight, they scale the learning rate. Okay, so this is what we have in a stochastic gradient descent, and now I'm scaling the learning rate by this term in the denominator. As you see, its formulation is similar to AdaGrad, but it has another formula. So what does it do? Again, eta here is for stability. Why? Because if v becomes 0, then I will have division by 0. Okay, so I will have eta again as a hack for stability, not to have division by 0, and this vk plus 1 is equation 35. Let's compare equation 34 and 36. As you see, they are very similar. Now, what is it doing? What is it doing? Again, it's saying that I want the idea is similar to momentum, and that's why it's called forgetting factor. Okay, I want to see how much I can forget my previous update, but my previous update in the scale of eta. See, momentum. What does momentum do? It says how much I forget my previous update for update of x. Okay, here it says how much I want to forget for the scale of learning rates. Okay, do you see the difference? Although it's inspired, but it wants to see how much I want to forget for scaling the learning rates. Okay, so This previous one, RMSProp, proposed by Hinton, not published. Adam was published. Adam, short, what is it short? It's not Adam and Eve, it's Adam. It's short for adaptive moment estimation. Okay, adaptive moment estimation optimizer, or ADAM. Reference 16. It improves over RMSProp by adding a momentum term. This time, it actually uses a momentum term. Okay. What does it do? It updates the scalar V. And so it defines two variables, a momentum term and a vector M, which is d-dimensional. D is the dimensionality of data. Okay. In neural network, D is the dimensionality of weight. Okay. And a scalar V. V is also a scalar. So do you remember? RMSProp was introducing a new variable V. Adam is introducing two new variables, M and V. Okay. And M is the momentum term. So you can see similar to momentum. M is updated in this way, equation 37. And V is updating as in equation 38. As you see, V is inspired by what? RMSProp. So it was a progressive thing. Every algorithm was based on the previous algorithms. Okay. So V was inspired by RMSProp, and M is newly added as this. Now we have gamma 1 and gamma 2 used in M, in update of M and V. They are both between 0 and 1. Then we normalize these variables in this way. So I use M hat and V hat rather than M and V in this way. Then they use this normalized M and V, or M hat and V hat, in the optimization updates. So this, let's take a look at this and this denominator. Let's talk about them. Assume I said, for now, let's talk about this one first. Eta M. Okay. Assume I set gamma 1 in equation 37. Let gamma 1 be 0. This term becomes a stochastic gradient descent. If gamma 1 is 1, it becomes the previous M. Okay. So it's a linear interpolation between M and what we have in a stochastic gradient descent. Okay. Now let's talk about this denominator. This is what we had in RMSProp. Okay. So see, the ideas are combined in this algorithm. Okay. The Adam optimize, which is a stochastic gradient descent with momentum while using RMSProp. The Adam optimizer is one of the mostly used optimizers in neural network. Interesting. Okay. Let me, give me a second. Yeah, I think I have it here. Okay, now we want to code a neural network. So that's fine. Let me. So theory is enough now for a while. Let's code it. Deep learning is a combination of theory and code, but it's not only code. It's theory and then code. So let's do simple linear and nonlinear regression using feed-forward neural network. Then I'm gonna use, I think I'm using PyTorch as far as I remember. Yes, I'm gonna, so two currently well-known libraries for neural networks are PyTorch, also called Torch, and TensorFlow. Okay. Previously, we had some other libraries too, but I think that they went out of date. Also, Keras has been combined with TensorFlow. Okay. So Keras, TensorFlow, and PyTorch. PyTorch, as far as I know, I might be wrong, but as far as I remember, was developed by Facebook, and nowadays it's called Meta. Okay. TensorFlow was developed by Google. So they were competitors. They didn't want to use their own, the other ones' libraries. So they developed their own libraries. And that, at least several years ago, as far as I remember, PyTorch, most of the codes in natural language processing were in PyTorch. Why? Because Facebook was investing in NLP, natural language processing. But several years ago, Google was investing in image processing. So most of the codes in image processing, deep learning for images, were in TensorFlow in GitHub. I remember that. But nowadays, apparently people are moving toward PyTorch, okay, even for images, because there are some reasons for that. TensorFlow is a pain in the neck, really. It updates itself once in a while, and you usually get a lot of problems when you run the old codes, and then you need to migrate your code using tf.compats. something like that. And it's a very hard thing. But PyTorch doesn't have these issues. Also, it's very similar to working with NumPy. Okay, so the same way you work with NumPy and Scalearn and these things, very similarly, you can work with Torch tensors, right? Okay, so that's why it has become easier to work with PyTorch, but it's you can use any of them. You can use any of them. So here, let's have a simple linear and nonlinear regression using feed-forward neural network. Let's first import some packages. Here I'm using Google Colab. By the way, I'm not sure how much coding you know, but it's good to develop your coding. For coding in Python, there are several softwares. You can either I think the best one is VS Code. Okay, Visual Studio Code. So Visual Studio is not free, but its free version is VS Code, Visual Studio Code. Okay, that's one thing. And you can use VS Code for other languages too, like C, C++. But we use that for Python. So when you install your VS Code, then you go and install. So in addition to installing VS Code, you need to install Python. So there are two ways, depending on what you prefer. Some people install Anaconda, okay, also called Conda or Anaconda. Anaconda installs a lot of packages for you and is easier, I think, to work with. Some people, however, especially in some industries, when they work with Linux, they don't install Anaconda. They work with pip, PIP, okay, rather than Conda. It's just the preference, whatever you prefer. But sometimes when you work with Conda, and why do they work in industry with pip? Because they usually want to use Docker, okay? And in Docker works easier with pip, Python and pip. That's one thing. Docker is just when you want to have compatibility of your packages and libraries. So you install them in a Docker, and everyone can use that Docker in their own PCs. So you will not have problems and issues with incompatibility of packages. Why? Because packages get updated a lot, frequently. Okay, you want to lock them and give it to your team members, for example. That's one thing. So let me tell you everything that I know about practical things. So I told you that one. And okay, so when you are working with Anaconda, sometimes the package doesn't work well, or it crashes, or it has incompatibility with another Conda package. In those conditions, people usually, although they are in a Conda environment, they install that package using pip. So when you are working with Conda, you can still install some packages with pip. But if you are working with Conda, it's better to first try Conda for installation of packages. If it doesn't work, then use pip. Okay, that's one. But by pip, I mean PIP. By Conda, I mean CONDA. Okay, so that's one thing. And another thing is that when you code, you can code Python in two ways. Either in a Jupyter notebook. This is called notebook, okay? In this way, I will tell you the difference. Or in some IDE software such as VS Code, okay? So in VS Code, when you want to write a project or something solid, okay? You usually use VS Code in software. So you write your codes in modules and they call each other and these things. But sometimes you want to do a fast coding. You want to try something, or you want to do a homework or something. It's not a big project. Then you can use Jupyter. Jupyter has some cells where you write your code and you run your cells one by one, and they go to the history. So when you shut down your computer and you restart it, you need to rerun all of the cells again, okay? And you should be careful that sometimes you, for example, because assume you have 4 cells, cell 1, 2, 3, 4, and you have something in cell 3, okay? You run cell 1, then run cell 2, these go to history. Cell 3 will use the variables saved by cell 1 and cell 2, okay? But then you do something in cell 4, which impacts the history, but it's after running cell 3. After 1 hour, you run cell 3, but you have forgotten that what you ran in cell 4 changed the history. Then you might get some errors or some unexpected results. So you should be careful that although the cells that you have written are in the order, but you might not run them in order. You might run cell 1, cell 2, cell 4, then cell 3. So they impact the history. That's one thing. And for those of you who know MATLAB, VS Code, Jupyter is similar to the MATLAB command line. VS Code is some like M5. Okay, that's one thing. Now I'm using Jupyter. For Jupyter, you can use either Jupyter Notebook directly. That has some tricks to work with, or you can use Google Colab. There are other things such as similar to Google Colab tools, such as Kaggle. Kaggle also has similar thing. Okay, so there are some platforms where you can run notebooks. One of them is the actual Jupyter notebook from your own PC. One of them is Google Colab, provided by Google. One of them is Kaggle, and these things. So I'm using Google Colab. In Google Colab, when I want to install things. So here, for example, I want to install Torch. Rather than saying, as I'm showing here, rather than saying, so in regular computer, I should say pip install Torch. But in Google Colab, I need to have this sign at the start. What is this sign called? What? Exclamation mark. Pip install Torch. So I need to do that. Then it is installing that. Then I'm importing the package. So import Torch. So import in Python is like include in C. Okay. Import Torch. They don't call it PyTorch. They say Torch. Import Torch. Then with some other modules I need to import torch.nn as nn. When I say as nn, I mean import this, but name it nn. I want to use the name nn in my code rather than torch.nn. Okay. And also here you can sometimes say from this torch.utils.data, import these two, data loader and data set. So what do these mean? There are several ways in Python. I want you to understand everything in code and theory. So here I'm saying that torch.utils.data. What do I mean? These dots mean two things in Python. So either I have a torch folder, and then inside the torch folder, I have a subfolder utils. Inside that subfolder utils, I might have a code data.py. So as I said, these dots either mean they are folders inside each other, or they are a .py file. Okay. So here I think Torch is a folder. Then inside of it there's utils, and inside of that there's data.py. Dot also might mean some other thing too. So for example, assume as far as I remember, in data, you might have several classes. I think you might have class 1, class 2, class 3. No, I think, yeah. For those, you need to say from torch.utils.data, import class 1 or import class 2, import class 3. Okay, that's fine. So according to what I said, data loader and data set are two classes inside data.py file, inside the folder utils, inside the folder torch. Okay. Now, what is class? An object. Many of you might know that, but let's discuss it briefly with an example. So, as in philosophy, the theory of ideas or forms by Plato. What was that in Plato? In the ancient Greek philosopher, he said in theory of ideas, he said that whatever we see in this world is just an image of a true form or idea in the world of ideas. Okay, many of the religions were inspired by this theory of ideas of Plato. This is a discussion in philosophy. So, for example, I'm Benjamin. Benjamin is an instance of a human, true human, in the world of ideas. Okay, when you say a rooster, there is a true rooster there. We might have several roosters. These are all images of that rooster. Okay, this is the theory of ideas by Plato. You can take a look at that. That's interesting. So using that, we can understand class and object orientation. What is that? These true things that we have, they are like classes. Okay, they're stored in hard drive or some part of the RAM. Okay, when we run the code, they come to some part of the RAM. Okay, and then I make images or instances or objects of those classes, true thing, ideas, in another part of the RAM. Okay, so I have a true human class, for example. I make an object Benjamin inside my RAM. Okay, and then interestingly, when I make every idea has some attributes, like human can talk, human has a skin color, human has height, has weight, and these things. When I make Benjamin, I say it's a human, but I set its attributes. Benjamin is this. Okay, these are the characteristics of Benjamin. When I make another Jennifer, I make the characteristics of Jennifer. So okay, so we do the same when we make an object from a class. We set its attributes. Every class has some functions. These functions are also called methods, especially in Java. They call it methods. Okay, these methods do something. So when you make an object from a class, you can say, "Hey, object, do this function." For example, when you make an object Benjamin from human, you can say, "Benjamin, talk." Now Benjamin starts talking. Okay, so that's one thing. And then these functions can get some input. So for example, when you say Benjamin talk where? In the class, or Benjamin talk in when you are playing a game. Benjamin talk when you are talking to a friend. Okay, so every function can get some inputs and also can output some things. That's one thing. And yeah, I think all this. The method, there is one method which is called automatically whenever we make an object. And that's called the constructor method. Okay, this constructor method is the method which sets the attributes. Whenever we make an object. Okay, now we will see whatever I said so far. We'll see how we are going to use the objects of data loader and data set. So here, matplotlib.pyplot, this is for plotting in Python. I imported and name it as PLT. NumPy, I imported and name it as NP from TQDM, or also called taqaddum. Why? Taqaddum in Arabic means progress. Many of its developers were Arabs. That's why they called it taqaddum or TQDM. From taqaddum, import taqaddum. Why? Because it shows the progress bar. When you want to show it in the terminal, how much progress you have. Okay. Now defining the network. So did I run this? Shift enter, it runs the cell. I'm importing the packages. Yes, it's done. Now define the device. So usually we set we have the device. It's either CPU or GPU. Okay, here I say use the GPU, CUDA for GPU, if it's available. If not, use CPU. Okay. Then device is known. Okay, here we have class of neural network nn.module. So what are we doing? Let me run it. So here I'm defining the class, the true idea. Okay, defining a neural network, and this neural network is inheriting from another class nn.module. What was nn? It was torch.nn. nn stands for neural network. Okay. And nn.module has some characteristics, and this is I define a new class which inherits from that. What do I mean by inheritance in classes? Go back to the example of theory of ideas. I have a class of human. Also have a class of animals, for example. Class of human inherits from the class of mammals, for example, right? And note that whenever we inherit from something, we get its characteristics, but we might have additional characteristics too. Class of human inherits from the class of mammals. The way we give birth is the same as mammals. However, we have additional things. We can talk. Mammals can't. Right? We can think about our existence. We can think about death. We are the only mammals which we can think about our death, our own death. So we can have additional characteristics. Now, when we say super, we usually say super.init for initialization of whatever we have inherited from. Then I'm defining the layers. Take a look at that. Self.layer1. When I say self, what do I mean? It means that refer to myself. Whenever I make an object, it has its own self. Benjamin has its own self. Jennifer has its own self. Jennifer's self is not referring to me. So self.layer1, then nn.linear. This nn.linear is being inherited from nn.module. nn.linear, so it's a linear layer. It is a dense layer, fully connected layer. And its size is 1/10. So it's 1 neuron to 10 neurons. And then layer 2, 10 neurons. So these two 10s should be equal. 10 neurons goes to 20, then 20 goes to 10, then 10 goes to 1. So it's a neural network which goes up, becomes larger, and then becomes smaller again. Then I also define ReLU activation functions, which we talked about. Do you remember? We talked about ReLU1, ReLU2, ReLU3. They are all instances of ReLU and ReLU class. Okay. Now, as you see, each of these layers are objects of linear, and each of these are objects of ReLU class. Now I have a forward method inside the nn.module. What is that? It shows the structure of the neural network. So here I say, get the input x, okay? Then pass it to the function self.layer1, then pass it to the function ReLU1, then get x again. What does it mean? Feed it to the layer 1, feed the output of layer 1 to the ReLU1, then this gives me x. Then this new x is fed again to the next layer, layer 2, then ReLU2, x, then layer 3, ReLU3, x. Then at the fourth layer, I don't use any activation function. Why? Because I want to do regression and it's unbounded. If it's bounded, then I can use, for example, sigma or hyperplane tangent activation function, but it's unbounded, so I don't use any activation function and return x. Okay, did I run it? Yes. Then now I defined the neural network class. Let's make an object of it. Net is the name of neural network is human. Net is Benjamin. net is an object. Then I print net, you can see here it is. Okay. Now optimizer. We learned all of them, the theory of all of them. Adam or SGD. Which one do you want to use? I say I want to use Adam. So if you want to use Adam, then you need to use torch.optim.adam. Otherwise, torch.optim.sgd. Optim, short for optimization. Then nets.parameters, you give the parameters of your neural network, which you just made an object to it. And this is LR, stands for learning rate, eta in our slides. Here is eta, and Adam adapts this learning rate as we talked about. Okay. Then the loss function, there are various loss functions in torch.nn. One of them is the class mean squared error loss, MSE, mean squared error. Okay, it's the same as least squares error. So loss function is this. Why am I using the mean squared error? Because I want to do regression. If I wanted to use classification, I had to use classification loss functions such as cross entropy. And then I ran it. Now that we defined the neural network, it's time to define the data loader to feed it to the neural network. Data loader. We define a class data inherited from data set of torch. Okay, so this is the constructor. I told you what constructor is. So it gets x and y as input. Okay, so we have function torch.from numpy. What does it do? It gets some numpy. Now in Python, working with vectors and matrices is numpy. Okay, whenever you want to work with vectors and matrices is numpy. But if you want to have numpy, but you need to convert it to torch to be able to use it in torch, right? In PyTorch network. So from numpy, this input should be a numpy, and it is. X is, I'm assuming x is numpy, not torch, and I reshape it. Why do I do that? Assume it's either 2D, an image, I want to reshape it to become a vector, or it's even a vector, but I want to make sure that it's a column vector. When I say -1 and 1, it means that it should have one column, and I don't care about the number of rows. You calculate it. Okay? So the number of rows times the number of columns should be the whole number of dimensions, right? So when I say -1, I say torch. I'm lazy to calculate, and I want to be parameterized. I don't want to write a fixed number. So you calculate it. And then dot float. Why do I do that? So after converting to torch, because I want the torch to be float, like float numbers. Okay. Then this is for data. This is for label, x and y, x data, y label. Here my labels are continuous because it's regression. Okay. I need to define these for data. One of them is len, one of them is get item. What are these? So whenever I have an object of data, when I say give me the length of that object, it will call this. If I don't define this, it will use the length method in data set. But I'm overwriting this. I'm saying that use my length function rather than yours. Okay. So what am I saying? That give me the length of data. You can write whatever you want. Someone might say, give me the length of data plus the length of label squared. You define that. But it makes sense to say, give me the length of data, right? And get what is get item? You have the object of data. Give me the second item of this data, the third item, the ith item. Whenever you say, give me the ith element of that, this get item is called. Which one? Item is the index, right? Which one? Then I say, give me the item in the data, the item in the label, then return as a tuple. Okay, where the first one is point data, the second one is label. So it always gives me two things, data and the labels. So let me run these two. And now this load data set. So we need to define the loaders of training data set and test data set, right? Let's do that. Load data set, we have X train, Y train, X test, Y test. So these are numpys. Why? Because I'm gonna pass them to data. And in data, I assumed X and Y are numpy, which I converted to torch. So I have X train, Y train, X test, and Y test. I give it to data. I have train DS. I think DS stands for data structure. It's my name, doesn't matter. Then DS is an object of this class. Where was that? It's this class. Okay. So I'm passing this to the data loader. Data loader gets an object of data. Data loader is from the torch, which we imported. Okay. I pass this train DS to data loader. It also gets batch size. Why? In mini batch stochastic gradient descent, we need batch size. Also in Adam, in the slides, we talked about one sample, but you can have summation in the Adam, right? In the gradient of Adam to become mini batch Adam, right? So it takes the batch size, and then I say shuffle through. For the training, I want you to shuffle the data points and the batches. Okay. For the test, I set shuffle to false because I don't care. It's already trained, right? I don't want to change the order of test data. So I have train loader and test loader as the objects of data loader. I return them. So this is a function. I'm going to use that. Did I run it? Now, data set. Let me create some synthetic data set. You should either load your data set or make some data set, right? I'm making a data set. So here I have made two data sets. We'll see both of them. So here, if it is linear, I make some random points. It becomes similar to linear. We'll see that. I think I have plotted that. Here it is. So training points are red, and the blue ones are the tests. And yes, you can also X-train. I have reshaped them to be column vectors, and I have used PLT matplotlib for plotting them. Now let's train the neural network. First, let's call the load dataset function. For 1,000 epochs, let's talk about this first. Okay, let me train it. And so see, this is the progress bar. Why? Because I'm using taqaddum. Okay, let me talk about the lines of this cell. So n epochs is the number of epochs. Loss list is the list containing the loss. I'm gonna put the loss values inside of it. Then for epochs, so I have an iteration for epochs. An epoch means we defined that. Seeing all of the data points once, seeing all of the batches once. So for epoch in taqaddum range, by the way, this is the description of taqaddum written here, epochs. And range n epochs, it means goes from 0 to n epochs minus 1. Okay, then inside the iteration of epochs, I need to have iteration of, you tell me, iteration of batches, right? So this is the iteration. So it's a nested iteration, nested loop. For step, then here I'm using enumerate. What is this enumerate doing? This enumerate says, so train loader, when you call it, it gives you data batch and label batch. Why? Do you remember? This was the output of the data loader. Two outputs, train and, sorry. Here. Where was that? There, here it is. Get item, data, label, right? Two things. It gives me two things. And that's why I get data and label, right? And what is this step? This is the index in this iteration because of enumerate. Enumerate also gives you the index. So data batch, label batch. For the data batch, I need to bring it to the device, either CPU or GPU. Okay, I need to bring it. If it is in CPU, I need to take it from the CPU and put it in the GPU, right? Label batch to device. So they are now in the device. Then I feed data batch to the net, which was the object of neural network. It gives me the output prediction, output of neural network. What does it do, this net, when I do that? It calls the method forward. Where was it? Forward. So it gets X, it passes through all of the layers of the neural network, it returns the output. So where were we? Here, net prediction. Now I have prediction, I have the label batch too. So loss function, what was that? Do you remember? This was the object of mean squared error loss. Where was that? Here it is. The object of mean squared error loss. And mean squared error loss, if you see its instruction on the web page, it gets, I never memorized that. It gets prediction first and the actual labels second. Okay, you can see its data sheet. And last function, it gives me the loss. Then if you want to record the loss and in a list, then you need to use append. Then, but this loss is in Torch. I need to, if it is in GPU, I need to first bring it to CPU, and then detach from the CPU or GPU, your device, then item. Why do I use item? Because this loss is a list of torches with one item. Okay, this item removes the list and becomes only the number inside that. So assume it's a list of 3.2. I want only 3.2, not the list of 3.2. This item does that. Okay, so I have the loss, and then this optimizer 0grad. Why do I do that? This is important in PyTorch. Before every step of optimization, iteration of optimization, you need to make the previous gradient 0. Get rid of the history of the gradients. Otherwise, you will have issues. So it will not be accurate then. So 0grad, this is not important not to forget. And then loss backward. What is it? This is backpropagation. These two lines are backpropagation, which we talked about, backward and a step. Optimize a step is a step of gradient descent. Here it's a step of Adam, right? A step of Adam. So then I also append the mean of the losses because I have a bunch of losses for the batches, and then I take the mean average. So taqaddum also shows the progress bar and this taqaddum, by the way, this is the time which has passed. This is the time which has been remained. Okay, and this is an average iteration per second. So did I run it? Yes. Then test. In test phase, prediction list. So with Torch no grad, this is important. So in the test phase, we don't need gradients anymore, right? We are not training. Gradient was using gradient descent on Adam and these things. So we have to say Torch no grad. Hey Torch, don't use grad. Inside that, I use a for loop for test loader now. Okay. It gives me data batch and label batch without shuffle because I set shuffle to false. So then I pass it to net. It gives me prediction. I put the predictions next to each other in a list. I ran this. Now let me visualize them by matplotlib. You see this? So these blue ones are the actual labels. So by the way, my data is one-dimensional. So X is data is one-dimensional. Its label is also one-dimensional. So I can plot Y versus X in this way. And the blue ones are the actual ones. The green ones are the prediction ones. As you see, it has been predicted them or regresses them very well. And for example, for this blue one, for X about 0.6, for example, it's here. It predicts this green. Do you see my cursor? Although there is an error, but the error is minimized because of mean squared error minimization of mean squared error loss, right? So as you see, it's very good. Now let's see the result for nonlinear data set which I made. This is my nonlinear, such as similar to sine cosine test train. I need to run this again very fast. Train again. By the way, you can plot the loss and you'll see the loss, especially for big data sets, it goes down gradually, okay? And test loader, and then plot it. No, something is wrong. It was working previously. What happened? I think, again, the problem of cells, I think something has happened because of that. Hopefully it works. I remember it used to work. I don't know what is the issue, but it used to work. Okay, sorry about that. But yeah, that's let's have a break and come back at 9:15. 10 minutes of break, please, and then I will continue. Okay, great, thank you. Okay, now. Okay, now let's talk about regularization in deep learning. I assume that you have watched the videos on the regularization and overfitting, which I have uploaded to my YouTube channel. If you are watching on YouTube, please pause now and go and watch that session and come back. So, okay, so regularization in deep learning. As I said, the prerequisites for this lecture is the lecture of overfitting and regularization on my YouTube channel. The name of that video is Overfitting, Cross-Validation, Regularization, and L1 and L2 norm regularization in machine learning, right? Okay. So the link of video is this, and please see the lecture before this. Weight decay. So these are in deep learning now, okay. Recall that L2 regularization from, recall the L2 regularization from the lecture of overfitting. What was that? This was equation 1. If we replace the objective variable X with the vector of neural network weights W, we'll have this. So in that lecture, I think that optimization variable was X. Now we have W as the weights, okay? So this is the actual cost or actual loss function without any regularization. In weights decay, we add this. What is this 2 in the denominator for? Because this L2 squared L2 norm is W transpose W is quadratic. When we take derivative with respect to W, it becomes 2W, and I want the 2 to be cancelled with the 2 in the denominator, okay? And this alpha is a regularization parameter, which weights how much the regularization term or the penalty term is important with respect to compared to the actual cost J. Okay, and so now let's continue. Why am I doing that? Why am I doing that? Penalizing the weights. So I'm penalizing the length of the weights, right? With regularization is referred to as weight decay, references 2 and 3. This penalty prevents neural network from becoming the weights of neural network from becoming too nonlinear and complex and thus overfitted. Why? Because when W becomes large, it makes the neural network very nonlinear. There is a reason. There is a reason. In activation functions, when for example, consider the hyperbolic tangent. Okay. Around 0 is almost linear. Okay. Around 0 in activation functions, around 0 are very almost behaving like linear almost. But when they have large X values, like here or very minus negative value, so here, either here or here, they become highly nonlinear. Okay. So it means that when the weights are very large, so the outputs of the layers become very large, So the inputs of the activation functions become very large. I mean, by very large, I mean very positive or very negative. Okay. So the output of activation function is very nonlinear. Okay. It becomes, therefore, for large W, the network becomes very nonlinear and too complex. Okay. And complexity means overfitting. Do you remember? Okay. So I want to prevent overfitting. The reason is that, as I said, according to the nonlinear activation functions such as hyperbolic tangent, very large weights, very positive or very negative, are in the very nonlinear parts of the activation functions. Okay. Although neural network should not be completely linear in order to be able to learn nonlinear patterns, although it should not be linear, right? If it's linear, then it can't handle nonlinearity of data. But I also don't want to become too nonlinear to be overfitted. So it's a trade-off again between being linear and being nonlinear. Being linear can't handle nonlinear data. Being too nonlinear becomes overfitted to the training data. So a middle case scenario is good, which is the regularization like this, weight decay. Okay. So, but it should not be very nonlinear as well, not to be overfitted to the training data. That's fine. Okay, penalizing the weights makes the weights relatively small, right? Because if W is very large, the regularized cost in equation 1 blows L2 norm of W gets large, right? So where the activation functions are almost linear, because W is small, to have a balance in linearity and nonlinearity. In the lecture of overfitting, we proved that the result of equation 1, we proved that is this. Okay. So what was UN lambda? UN lambda contained the eigenvectors and eigenvalues of Hessian of J. What was J? The non-regularized or actual cost function, right? Okay. And UN lambda were the eigenvectors and eigenvalues of J, of Hessian of J. W star is a solution of non-regularized problem. If you minimize only J, its solution is W star, which is here. W dagger is a solution of regularized cost, which is J plus alpha over 2 squared L2 norm of W. Okay. It has similar interpretations as we discussed before in the lecture of overfit. Okay, we talked about it. So I think weight decay simply this analysis is the most important analysis of weight decay. I want W to be small enough so the input of activation functions are almost in the linear range, not too nonlinear. Noise injection to input in neural networks. This is another regularization method in neural networks. And what does it do? So in training neural networks, it is beneficial to add noise to the input. Okay. So when you have data, rather than giving the raw data, add some noise to it. This is a way to avoid overfitting. This is a regularization technique in deep learning. So one perspective to why adding noise to inputs helps better training of neural network is data augmentation. Okay. Assume rather than just data, I give data and data plus noise. So I'm augmenting to my data. Okay. Data augmentation is useful for training deep neural networks because they have a huge number of weights, the neural networks, right? And if we do not introduce enough training data to them, they will overfit to the training data. I think here, yes. Let me think a bit. Yes. So when you have a neural network, okay, if you don't have enough number of parameters, number of weights, what happens? It will underfit because you don't have enough complexity in your neural network. And if your data is complex, it's not enough. It's underfit. Do you remember we talked about underfitting and overfitting in that lecture of overfitting? Okay, it will under. So we need to have more layers, increase the number of neurons to have more number of parameters in order to be able to handle complexity of data. However, The more we add to the parameters, the more is the risk of overfitting. So there, again, there is a trade-off. Too low number of parameters has a risk of underfitting. Too huge number of parameters has a risk of overfitting. A middle case scenario is good, which is a good fit, right? So when we increase the number of parameters, it has a risk of overfitting. How can we prevent the risk of overfitting here? By having more data. So when you increase the number of parameters, the layers and neurons, so you will have more number of weights, right? For training these number of parameters, you need more data. Otherwise, you will overfit to that small data that you have. Okay, that's the reason why that data augmentation is used. Let's augment to the data, add to the data. Okay. Another interpretation of noise injection to input. So one interpretation was data augmentation. Okay. Another one is regularization. Okay. So you can see it in this. Assume that the optimization of neural network is this: minimize J, which is expectation of y hat of x minus y squared. This is mean squared error, right? So this x is input of neural network. Y hat of x means out prediction of neural network for x, input x. Y is the actual label of x in the data set. We want to minimize the distance between the squared error. Okay, and expectation means the average here. Okay, so this is mean, average, squared error. Okay, I told you that. So we add noise. I'm talking about noise injection to input, right? So I'm introducing noise here. We add noise epsilon, and let epsilon be a Gaussian noise. Okay, with mean 0 and variance sigma squared, and let the covariance matrix to be diagonal. So it's like a hypersphere in this space. In all dimensions, it has the same variance, amount of variance. It's like, okay, it's like a ball to the input, so that the objective function changes to this. So rather than input x, I have x plus epsilon, right? Okay, so I'm adding noise to the input. Now what happens? Let's use the binomial theorem. A plus b squared is a squared plus b squared plus 2ab. So the here is minus, so a squared plus b squared minus 2ab. So the first term is squared. Note that this is the input. This doesn't get a squared. This is the input of neural network. The y hat gets a squared. The second term is squared minus the first term, the second term. Minus 2, the first term, the second. Okay. Now expectation is a linear operator. So I can write every term with expectation. And 2 is a scalar, so it can come, it's not random, so it can come out of expectation. Okay. Now, assuming that the variance of noise is small, the Taylor series expansion of y hat x plus epsilon. Let's see. Y hat x, what does it mean? The output of neural network for the input x plus epsilon. What is this Taylor approximation? For the second order Taylor approximation. So if we can write it as y hat x plus epsilon transpose gradient of y hat x with respect to x plus 1/2. This is the quadratic term. 1/2 epsilon transpose second derivative of y hat of x with respect to x epsilon. So it's quadratic with respect to both x and the gradient. All right, plus some other terms. O epsilon cubed. Okay, the small o. So this is a Taylor series approximation. Now, this is what we had. Also, we found J tilde. So we found these, so I'm repeating them. So this was J tilde that we just talked about, and this is a Taylor series approximation. I'm repeating them here in this slide. Okay. Now, what do we have? This was J tilde. J tilde, I can, so here, let me think. Give me a second. Give me yes. So this is y hat x plus epsilon. I have y hat squared. So this is y hat x plus epsilon, but a squared. Okay, squared, y hat squared. And this second term is here. This second term is here. This is the third term. Correct? Okay. And as you see, I have y hat squared x plus epsilon here. Also, I have y hat squared y hat x plus epsilon. So I'm replacing both of these y hats with their Taylor series expansions. Here and also here. So here, as I see, I have y also multiplied to that. So here, y is multiplied to its terms. Okay, is it obvious? So y is multiplied to its terms. Now what happens? Here, I use, give me a second to recall. The first term, I'm using the inverse of binomial theorem. So I'm using a squared plus b squared minus 2ab. I write it as a minus b squared. So let me recall. I need to think a bit. What were we doing here? I forgot. Oh, okay. I think I now get it. Sorry, as this is mathematics, I can't memorize this. I need to think about them. So here we have what? Minus 2, these and these, plus, if you guys can help me, I appreciate it. Okay, I think I have explained in the below. Okay, as I have epsilon is noise, Gaussian noise with mean 0 and variance sigma squared, do you agree that expectation of epsilon transpose epsilon is sigma squared, right? Do you agree with that or not? Recall preliminaries. As the noise and the input are independent, the following term is simplified. So here, see, I can write this. This is a squared, right? So I can write it as this epsilon squared and this term is squared. But as it is a vector, I need to get a squared L2 norm. Why can I have this expectation of this times expectation of this? Because they are independent. Noise is independent from the gradient, right? Is noise dependent on the gradient? No. So I can write it as multiplication. This expectation of epsilon transpose epsilon is sigma squared, as we talked about it here, and I have it here. Okay, let me, the rest of the expression, I don't have enough concentration to recall what was here. Let me think. No, that was something else. The first term, okay, the first term. Even if I can't find out right now, in the next session, at the start of next session, I will tell you. I need to think about it, but I don't have enough concentration to figure it out. Okay, but so anyway, we simplify this. In the start of the next session, I will explain the proof again. I need to think about it. Okay, the overall loss function after noise injection. So what we had as J tilde here. Okay, with some proof which I skip right now, we end up with equation 4, right? Okay, what is J before regularization, right? So and the rest of the terms I think is obvious. Sigma squared is the variance of noise. Y hat of X is the output of neural network for input X. Y is the label. And this is the second derivative of Y hat of X with respect to X. And this is also the gradient or derivative, first derivative of Y hat of X with respect to X. It's L2 norm, a squared L2 norm, expectation, which means the mean, okay? This penalty, the penalty is on the second derivative of outputs of neural network, where I mean this, okay? This means that we do not want to have significant changes in the output of the neural network. Is it obvious? What does this mean? The whole thing here is the regularization term. Do you agree? Do you agree? Guys, I just missed one proof. But don't get disappointed. I also get tired. So accept this from me. Later, I will tell you why we can come up with this. Let's interpret that. This J is not regularized. The rest of the terms are regularization terms, okay? Now, I have considered these two. I have derivative of Y hat of X and second derivative of Y hat of X. What does it mean? What is derivative? It means how much change I have. So when I penalize that, it means that I don't want to have much change. If I change the input X a bit, I don't want the output of neural network to change hugely. That's exactly means that I don't want to have huge variance. So I don't want to get overfitted, because overfitting means that I have huge variance. Do you remember? High variance, low bias. Did you understand why noise injection helps us not to overfit? That's the reason. Because we are penalizing overfitting. We are penalizing variance of output. Okay. Note that the technique of adding noise to the input is also used in denoising autoencoders. Why? Let me briefly talk to you about the autoencoders. So in autoencoders, we have some encoder and some decoder. So encoder gets the input, encodes into some features. The decoder gets these features and reconstructs the output or output something, okay? If we train this autoencoder, so this output is similar to its input, it becomes a reconstruction autoencoder. We have some other autoencoders too, okay? Its output might be something else, but we usually in autoencoders, we want to reconstruct the input, okay? Then we have multiple scenarios. Either it's this way or this way. Okay, this left-hand side, this is under complete, guys. This is under complete autoencoder. This is over complete autoencoder. So the number of neurons, the number of features in the latent space here, in the over complete is larger than the dimensionality of data. In under complete is smaller than the dimensionality of data, right? So in under complete autoencoder, we are compressing data. In overcomplete, we are not. We are expanding data. But you tell me, if I introduce some X and I also want it to reconstruct X hat, if I use overcomplete, what happens? If you are put yourself in the shoes of autoencoder, assume you are the weights of the neural network autoencoder. what would you do? You yourself are an over-complete autoencoder shown here. What do you do to reconstruct that? The easiest way. You will just copy. Because you have enough number of neurons in the middle layer, more than the input layer, you just copy some of them to some of the neurons. So for example, each data is copied to one of the neurons. You have more than enough neurons in the middle layer. It's not compressing. If it's compressing, it can't copy because you don't have enough number of neurons in the middle layer for every dimension. But for overcomplete, you can. You can cheat, you can copy. So if human does that, therefore neural network also learns in this way by gradient descent. It will copy. For overcomplete autoencoder, in order not to have this way, not to copy, not to force neural network not to copy, you will say you will give X with some noise, then we will reconstruct the not noisy data. So we'll give X plus some noise, epsilon, but your output should be X hat, not X plus epsilon hat. Therefore, this can be used for denoising. This is called denoising autoencoder. Right? This is called denoising autoencoder. As I said, this can be used in denoising autoencoders too. Moreover, an overcomplete autoencoder with one hidden layer, where the number of hidden neurons is greater than the dimension of data, needs a noisy input, as I told you. This I explained already. It is also noteworthy that injecting noise to the weights of neural network can be interpreted similar to injecting noise to the input. It is possible to do that. So rather than injecting, so far what we talked about, we injected noise to the data, right? Now, let's not inject noise to the data. Let's inject noise to the weights of neural network. This is also a regularization technique. Okay, noise injection to the weights. Okay, therefore, noise injection to the weights can also be interpreted as a regularization where the regularization penalty term is this. Now, note that this regularization term is derivative of output of neural network with respect to W this time. Note that these two were with respect to X. Why? Because I was injecting noise to the input. If I inject noise to the weights, the regularization term will be with respect to W. Okay. Early stopping in neural networks. As we mentioned in the explanations of overfitting lecture, we train neural network up to a point where the overfitting is starting. Do you remember? So here we are underfitted. Here we are overfitting. Why? Because error of training always goes down almost. With some oscillation might go down. But after a while, the error of validation, which is not used in training, goes down, 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 and suddenly it starts to go up. This capital error or the error of validation, you can see it as a generalization error because it shows how much you can generalize to unseen data during the training, right? This is a good fit. So this is overfit, low bias, high variance. This is underfit, high bias, low variance, but you want to stop here. So early stopping in neural networks tells you stop at the right moment. Why can we do early stopping in neural network? Because it is an iterative algorithm. So assume, do you remember this x-axis was model complexity? You can see it as the iteration index or epoch index, whatever you call it. Iteration index. Why? Because the more you train, the more complex your neural network becomes. Okay? As the more you train, the more complex it becomes. You can see this axis, x-axis, as the iteration index. So at some iteration, this is a good fit. Stop. This is called early stopping. References 10 and 11, which helps avoid overfitting. Okay, and this figure also, we talked about it in the lecture of overfitting. We were saying that why using Shor, Stein's unbiased risk estimator, we were saying that why this happens, why this validation error goes up after a while. Okay, recall the overfitting lecture. This a regularized optimization is this. The L2 norm regularization is also referred to as ridge regression or Tikhonov regularization. Tikhonov is I think is a Russian scientist. So suppose W star is a minimizer of J. Okay, suppose W star is the solution of not regularized optimization. Okay, the Taylor series expansion of J up to the second derivative of at W star is this, right? Why? So here, why don't I have the first term? Because in the lecture of overfitting, we already talked about it. The first term has gradient of J W star, and we know that by first order optimality condition, this is 0. This term is 0. Because at the optimal solution, what do we do in first order optimization? Take derivative, set it to 0. The first order optimization at that point, the first order derivative at that point is 0. So in this Taylor series expansion, I don't have this term anymore. Okay. If we apply eigenvalue decomposition on the Hessian matrix, I will have this U delta U transpose. I think you are tired, right? So let me in the next session, I will wait. In the next session, what the first thing that I will do, the first thing which we will do, we will go over the proof of noise injection to input that we skip, and then we'll continue this lecture slide deck to cover regularization techniques in deep learning. So in summary, I can tell you there are several techniques in regularization in deep learning for regularization. And what do I mean by regularization? I want to avoid overfitting. One of them was noise injection, one of them was data augmentation, one of them is early stopping, and these techniques. We will finish this in the next lecture, and then afterwards, this is the agenda in my head at least. We'll cover a convolutional neural network and its philosophy. It has mathematical philosophy behind it, okay? And afterwards, we will cover, is in my head, I have this agenda. Some important convolutional networks, such as ResNet, AlexNet, and these things. Some of them are less important, some of them are more important, such as ResNet, UNet, and these things. Some important things. And afterwards, after covering ResNet, UNet, and these things, we might see some of their codes. Afterwards, we'll go and talk about sequence-based data. We'll cover recurrent neural network, RNN, LSTM, long short-term memory networks. Afterwards, we'll go to the state-of-the-art sequence-based neural networks, which are attention mechanisms, transformers, BERT, GPT. I think you know ChatGPT, right? And the rest of the agenda will be, I think, with different orders. I will need to decide about the order, but it will be deep reinforcement learning and the other things which we talked, such as saliency map, explainable AI, and these things. Okay, this is the agenda. So after regularization, we'll cover convolutional neural networks and important CNN networks such as ResNet and these things. Okay, thank you. Thank you.